Okay. So first I want to thank the organizers for the opportunity to speak at this conference. And I'd like to talk a little bit about what the status of naturalness and the hierarchy problem is, and in particular an approach to it which goes by the name of neutral naturalness or colorless top partners. So the question is the discovery of the Higgs and the fact that we haven't seen anything else at the LHC the end of the idea of natural theories of the electroweak scale? Are we just giving up on naturalness? And then the question is, so we have already even experimentally seen that we have the weak scale, but then there is a scale determined experimentally by direct and indirect bounds, which is already at the few TeV scale here, which is telling us that what we have here in this gap between the weak scale and a few TeV is the standard model, but it's tuned to some extent. And so this is what we call the little hierarchy. And then the question is, this is already established experimentally as a problem. We haven't seen anything beyond the standard model. And so there is an extent to which the standard model is already experimentally determined to be a tuned theory to some degree. Okay? And then the question is, the quadratic UV sensitivity on the Higgs mass is dominated in particular by the top contribution to the Higgs mass square. And typically what we do in order to cure this in natural theories of the electroweak scale is to impose a symmetry, and this symmetry will, among other things, relate the top quark to its partner under the symmetry, and this partner will have a one-loop contribution to the Higgs mass square, which will cancel this quadratic sensitivity to the UV scale. Now, typically in the theories we consider for the past 20 years, the top partners carry color, and then they are easily produced at the LHC, and this results in these stringent bounds for the most part. So the point is, can we build theories where the top partners do not have SU3 color, and therefore they're harder to have been seen at the LHC? So if the symmetry protecting the Higgs mass does not commute with SU3 color, and it exchanges into another SU3, let's call it SU3 prime, then these top partners will be charged under this new color. The bounds will be less stringent, and the hope is that these theories with colorless top partners will be more natural than the extensions of the standard model we have today. So essentially the idea of these theories of colorless top partners or neutral natural theories is to fill this little hierarchy gap with the standard model plus at the minimum colorless top partners, so as to solve at least the hierarchy problem or the little hierarchy problem here. Eventually, most of the theories, or all of the theories we have thought of act this way will have a cutoff not far above this scale of the few TeV. So how do we do this? So what are the ingredients for a neutral natural theory or for a theory with colorless top partners? Well, first of all, you need a symmetry protecting the Higgs, just like any other theory protecting the UV sensitivity of the Higgs mass. It could be that the Higgs is a pseudo-Nambu-Goldstone boson. It could be a version of supersymmetry. But you also need to extend the color gauge symmetry to have at least 2 copies of SU3. Okay? So it could be SU6 broken down to SU3 square, or it could be 2 copies of SU3. We'll see some examples. And then you either impose a discrete symmetry, or somehow you are going to extract the degrees of freedom by some procedure that can be generalized as orbifolding, such that the top partners will actually have the other color once we extract the light degrees of freedom of these theories. Okay? And the theories that have been worked on are old to begin with. I'm going to talk about the twin Higgs and folded supersymmetry, but there are also, as you see, any solution to the hierarchy problem can be turned into a colorless top partner type theory by these kinds of procedure. So if you just pick your favorite theory, for example, there is a little Higgs version called the Quirky little Higgs. And so as you see, these theories are rather old, 10 years or 9 years, but our interest is renewed in them because the situation of not having seen anything at the LHC. So let's just quickly review the twin Higgs. Is the 10th anniversary of the twin Higgs, I guess. So the Higgs in this theory is a pseudo-Nambu-Goldstone boson of a spontaneously broken global symmetry. And so we start, for example, there are many ways to actually do this, but let's just start with the original way, in which the global symmetry is SU4 broken down to SU3. And so there are 7 NGBs, out of which there will be 4 that we'll use for the Higgs. And then, so here is the potential for this 4 of SU4 that I call H, big H. Now, the next step is to gauge a subgroup of this SU4, which is SU2A times SU2B. So now the 4 can be split in these 2 doublets. And we'll use this top doublet, HA, as our standard model Higgs doublet. Now, when we gauge this subgroup of SU4, the gauge interactions will break the global symmetry explicitly. And this will lead, generally, you know that this leads to quadratically diverging contributions to the potential of big H. So you compute those contributions from the gauge loops, and they are quadratically divergent. And so here it is. This is GA and GB are the gauge couplings of the SU2H, SU2B. And here are the cutoffs, lambda A and lambda B, which in principle, the behavior of the theory in the UV does not have to be the same. So in principle, however, if I impose a Z2 symmetry such that the behavior in the UV is the same, and then the gauge couplings GA and GB are the same, and also the cutoffs of the theory are the same since the Z2 is good in the UV, then it turns out that the gauge contributions to the quadratic divergent gauge contributions are of this form. So if you just get the cutoffs and the gauge couplings out, and then it turns out that this is SU4 symmetric. And so if you think of the Higgs as coming from the NGBs in this global breaking, then the Higgs do not enter H dagger H is SU4 symmetric, and so this will not contribute to the Higgs mass square. So this is essentially the philosophy of the twin Higgs idea. The imposition of this Z2 symmetry in the UV is what protects the Higgs from UV sensitivity. So if you extend this to all standard model interactions, not just the SU2 interactions, then essentially you have a standard model mirror sector. So we have the standard model A, which is us, the standard model B, which is the twin standard model. And for example, if you look at the top Yukawas, now you can write them in this way. In general, there is the A sector Yukawas and there is the B sector Yukawas that will generate these quadratically diverging contributions for the A and the B Higgs doublets. But if you impose the Z2, once again, the contributions from the Yukawas, the quadratically divergent contributions from the Yukawas are indeed SU4 symmetric and will not affect the Higgs mass square. There will be, yes, logarithmic divergence or logarithmic sensitivity to the cutoff because, well, I'm not going to the detail, but there will be contributions that go like HA to the fourth and HB to the fourth, and those contributions do have logarithmic sensitivity to the cutoff. But the quadratic sensitivity is all we care about here because we're trying to solve the little hierarchy problem. So if you go to the nonlinear representation, this becomes clear. Here are our 2 doublets, but I can write them as the Nambu-Goldstone bosons here exponentiating and some VEV F. Okay, and here in the Nambu-Goldstone matrix, will write the 4 degrees of freedom that I will use for the Higgs doublet, which is right here. Okay, and all the other the other 3 NGBs are eaten by the SU2B gauge bosons in this formulation. And so, so when you do that, you can expand the H matrix and rewrite the Yukawas and take the first 2 terms of the expansion, and you will see that the cancellation of the top, our top quadratic sensitivity to the Higgs mass comes from this term, which is non-normalizable in this nonlinear formulation. And this cancellation, the symmetry is just coming from this fact here, the fact that the Z2 symmetry imposes that the lambda A and lambda B aren't the same. And so, so this cancels the quadratic divergence to the Higgs mass, but the top partner, the B tops, are not carrying SU3B color. They are SU3A color. They're carrying SU3B color. So this is a colorless top partner solving the hierarchy problem for you. So, so up to this point, you have an exact Z2 symmetry. But if you do have an exact Z2 symmetry, what happens is that this VEV, or the VEV that parameterizes the breaking of SU4, will be the same as the Hicks scale, because essentially all the A sector has to be identical to the B sector. So our VEV and the VEV of the B Higgs, the twin Higgs, will be the same. So you need to break this, this Z2, but you break it softly by, for example, adding a term like this, a soft term like this, and this allows a hierarchy, a mild hierarchy between the electroweak scale and this F scale of the twin Higgs VEV. And typically what will happen, for example, for the phenomenology of the twin Higgs to start being explored, is that the couplings of the Higgs to standard model fields will be suppressed by the cosine of V over F, essentially, right? So V over F will be this small, there will be a small hierarchy in order to avoid bounds, essentially, that I'm going to show you now. If this was identical to our Higgs scale, if F was the same as the Higgs scale, then, for example, the invisible width of the Higgs will be, I don't know, 50%. So that's clearly excluded, right? So we need to break the Z2, at least mildly, in a soft way. So there are several incarnations that are used now for the phenomenology at the LHC. The one that is the original is now called the identical twin. It's a complete copy of the standard model. F over V goes somewhere between 3 to 10, where the 3 comes from essentially the invisible width of the Higgs, and the 10 is just a matter of taste and naturalness. This will force, for example, the twin QCD to have a strong scale which is somewhat above the QCD scale. You will have light twin quarks and leptons, and then the question is whether you will, for the model building, you will keep the twin photon massless, or you will have to break it. Then this is a question of, for example, cosmology, things like that. So this is the identical twin model. In the identical twin model, then, as I said, all Hicks couplings to the standard model states are suppressed by this cosine of V over F. In this way, for example, if rho is the Higgs, the radial state, our Higgs in the twin Higgs model, then it is the production with respect to the standard model and the decay to our sector states, W's, Z's, B's, etc. And then the invisible width will go like the sine square of this angle times the standard model width in equivalent states times some kinematic factor delta, which is less than 1 when essentially the masses of the B sector are heavier than our masses. Essentially, so you need this kinematic factor to account for the invisible width. And so as you see, when delta, as F becomes much bigger than the electroweak scale, delta becomes much smaller than 1, and you reduce the invisible width. That's the idea, right? So if you look at the Hicks couplings, so here in the green line, you see the invisible width as a function here of the top partner mass, but essentially you can see this as a function of also the scale F. The top partner mass is proportional to some extent to F over V times the top Yukawa coupling times the cosine, or the cotangent actually, of V over F. So essentially, if you just look at the current bound from the invisible width, you probably are around this area over here, which still leaves you with a tuning which is not too bad. It's 30% tuning for this theory. On the blue line, we see the signal strength for whatever channel of the Higgs that you can imagine, compared to the standard model, so the signal strength. And you see that you get to signal strengths that are around 5% of the standard model, and you still are around 10% tuning. So you could imagine that you will reach high luminosity LHC stages just by measuring the Hicks coupling, and then you wonder if you're going to be able to see, to exclude these theories just by looking at the Hicks couplings and excluding deviations. And if you are with a 5% signal strength, you still will have theories that are, this theory will still be around 10% natural, or just below 10% natural. So it is possible to imagine that the identical twin Higgs may still be around as not that fine-tuned, even at the end of the high luminosity LHC, which is of course terrible. But this is the nature of this model, right? Now, there is also another version which is more tailored to having signals, which is called the fraternal twin. In the fraternal twin, only the minimal fermion content to solve the hierarchy problem is considered. It's kind of like the twin Higgs version of natural SUSY. In here, you only have the third generation quarks and leptons. And then it turns out that the glue balls of this twin sector are the lightest hadronic states, and they cannot decay to light mesons because there are no light quarks in this theory. And so it turns out that these glue balls, the Higgs can decay to these glue balls with branching ratios that are, very small, 10 to the minus 3, 10 to the minus 4. However, these glue balls are typically long-lived in this model, and they can generate highly displaced vertices. So the hope in the twin Higgs models that have this fraternal twin type spectrum is that you will be able to see from this the case of the Higgs to these twin glue balls, these highly displaced vertices. So for this you really have to go to this fraternal twin setup. But other than that, you just look at you have to look at the Hicks couplings. Recently, there's been a lot of activity in the twin Higgs dark matter idea. Why is this interesting? Well, it turns out that the twin strong sector generates a higher strong scale by a little bit, as I mentioned earlier, which means that in the identical twin case, the twin baryons are a factor of a few heavier than our proton. And so this is very interesting for asymmetric dark matter model building. And in fact, there's some recent work by Marco Farina. And here you can see, assuming just essentially that this factor of a few is between 4 and 6, so you get 5. This 5 factor is if the mass of the twin baryons is 5 times our proton mass, then you will get the relic density you need for dark matter. And so in this case, you compute the cross-section in direct detection by using either higher dimensional operators or Higgs portal interactions. And this is what you get from 1 TeV higher dimensional operators down. And so you see that it's possible that this simple and natural idea of having a twin Higgs dark matter may be accessible somehow in the future experiments. Although if you just look at the Higgs interaction, is somewhere down here below the neutrino floor. But then there is some activity also for the fraternal twin Higgs. There are some papers here. There is also either asymmetric dark matter, which is typically what you want to do for twin bottom baryons. In this case, only the bottom will be your baryon because there are no other light quarks. This is a spin 3½ dark matter candidate, but you can also do thermal relic. In this case, mostly the twin tau would be the dark matter. So this is what the twin Higgs does for you, and so it's a difficult phenomenology if you really stick to the identical twin Higgs, and in principle. There could be some deviations in the Higgs coupling, but it's hard to see what the path to a smoking gun would be that will definitely get this model. Now, what about supersymmetry? Can we build a supersymmetric theory that does this thing, that has colorless squarks, so that you wouldn't have produced the squarks at the LHC? And the answer is not really, but yes and no. So let's see what does that mean. You know? So this theory goes by the it's not twin supersymmetry, it's folded supersymmetry, but that's, I don't know. There's a motivation that hopefully will be clear. So the idea is that, again, exactly the same. These quarks in the cancellation, we don't want them to have SU3 color. So how do we do this idea? How do we implement this idea that these quarks canceling the quadratic sensitivity to of the Higgs mass do not have color? How do we do this? So in order to motivate this idea, I think this toy example is all we need for technically. And this goes by the name of Byfall Protection. And essentially, this simple model is like this. Suppose you have a global UN, a flavor symmetry, which is this UN. So I have a singlet, and I have these fermions, which have that are fundamental of the UN. And then we have this simple coupling between the singlet and these fermions. And of course, in this setup, the singlet is quadratically divergent, has a quadratic sensitivity to UV scales. This is the obvious thing. So the first step to have bifold protection is to supersymmetrize the theory and to think of this as the superpotential. Okay? So fine, now you have some protection for supersymmetry in principle, if supersymmetry is exact. Then the second step, which is the bi in bifold protection, is to duplicate the flavor index between n to 2n. So now I have 2n in the loop that gives me the quadratic divergence. So far, it looks like a useless thing to do, but let's see what we do with that. The next step is to define a parity, which is actually an element of the global group. This global group, this U2n, now is instead of UN, I have a U2n flavor symmetry. This is one element of this group, and I pick this element with pluses in the diagonal up to from 1 to n, and with minuses from n plus 1 to 2n. Right? So this element will be define this transformation. And then it turns out that if you look at that superpotential, the theory is invariant under the following transformations. The singlet going to itself, the q's going to minus gamma q, and then the q bars going to minus gamma, well, this is the star, but this one is real, minus gamma star q bar. And also, the theory is also invariant under this Z2R, let's call it Z2R symmetry, where under which bosons transform to themselves and fermions to minus themselves. Okay? So now, so the theory is invariant under this, but now I'm going to ask that the states that are odd under the product of these two symmetries are projected out. So this is sort of like an orbifold projection. You can think of this as being an extra-dimensional theory, and this would be like a boundary condition. So I'm going to say this will be like a boundary condition projecting out states that that are not even under this product. So here is the Z2 gamma. So here I have the fermions from 1 to n, and from n plus 1 to 2n. So gamma hits them with a minus 1 here and with a plus 1 here. And the scalars, as I said before, because of this Z2R, are even here and odd in the fermions. Okay? So here so now the product of these two has to be positive. And so what happens is now that this mechanism essentially selects the fermions with indices between 1 and n. So these guys will stay in the spectrum at low energies, and the scalars with n plus 1 to 2n indices. So now I have this theory that is, in principle, not supersymmetric anymore, because these q1 to qn are not superpartners of the qn plus 1 to q2n scalars. However, what I have now is that, so this is my low energy spectrum. I orbifolded out or modded out all the rest of the states, and I ended up with this in the low energy theory, but still I have in the loop the fermions from 1 to n and the scalars from n plus 1 to 2n cancel each other's quadratic divergences, and the theory is UV insensitive, at least quadratically, to one loop. Okay? So this is the mechanism of Byfall protection, and it's inspired in the large N orbifold correspondence that was proposed by these people many years, almost 20 years ago. So this allows us to construct then a theory that has at one loop no quadratic sensitivity in this singlet, in this scalar particle, but it's not supersymmetric. There is some sort of accidental supersymmetry in the low energy spectrum, but not real SUSY. Okay, so in that sense, it's no SUSY, but some leftover supersymmetry is there. Okay, if you think about it, at two loop, this doesn't work anymore, right? For example, the scalars are not protected by this symmetry. The scalars themselves will be quadratically sensitive. If I open this loop of the scalars and I close the singlet, the mass of the scalar will diverge, will have a quadratic divergence. That means that if I have a two-loop contribution to the singlet, it also will have a quadratic divergence to the singlet at two-loop. But I don't care about two loops. I only care about one loop because I want to solve the little hierarchy problem. Two loops will be important above that scale of few TeV. So to implement this, then, all I do is now I have to, of course, do this in the real world. So now I'm going to have my 3 copies of SU3, my Z2 that relates the SU3 couplings in the UV, and then the weak sector I'm going to leave untouched. And I'm going to assume that the orbifold in some extra-dimensional theory gives me the fermions of our sector with our color, but the scalars with the wrong color. And essentially, this leads to these interactions in the top Yukawa, which still protects Higgs mass squared to one loop. Okay, so this is the setup in extra-dimensional theories. I have no time to talk about it, obviously, and so SUSY is broken in an extra-dimensional setup by boundary conditions, and then essentially I end up with this spectrum. This hypermultiplicity leads to our fermions, and these hypermultiplicities will have scalar zero modes with the wrong color. Okay, so this is what we do. The interesting thing that I do want to point out is that the scalar masses are actually calculable in this theory, and this is very old calculation from these people, because essentially what happens here is that SUSY breaking is non-local. Essentially, in this setup, we have an n equals 2 supersymmetry in the bulk, and then you have n equals 1 supersymmetry in this fixed point and in this fixed point, but these two n equals 1 supersymmetries are different. And so the low energy spectrum sees a broken SUSY, but in order for the zero modes to acquire masses, I will have to go from this point to this point, so I see the different two n equals 1 supersymmetries, and then I realize SUSY is broken. And so this gives me this sort of a calculation of the masses. So the masses are several hundred GeV if I assume that 1 over R, for example, is a few TeV, is my E bounds, right? That's all this transparency says. So this is the setup. I have accidental SUSY between, say, a few TeV and a weak scale, but then there will be a 5D SUSY, and eventually it's a cutoff because this is a non-normalizable theory, and there will have to be a UV completion. Right? All of these theories, the twin Higgs, Quirky little Higgs, folded SUSY, they have a cutoff which is not very far from this few TeV scale. So they require UV completions to become actual real theories. And that's an important thing. I don't have time to talk about signals, but there are signals, and I'm just going to say that the fact that I have an SU3 that confines the SU3 prime, and that the quarks are hundreds of GeV, it means that they don't hadronize. Okay, so these guys will have Quirky type behavior. They will generate sort of a global radiation as well as a photon radiation. They will have to come back to each other and annihilate, and from there you can get bounds, which are right now at the 450 GeV level. So I'm going to skip this, and I'm just going to summarize. So we still have natural theories of electroweak symmetry breaking that are not ruled out by data. It's true. The signals at collider are different. I didn't have time to talk about this, but for example, in folded SUSY, glue balls can be produced both in this quark production they will emit it, and also Higgs could decay to them, and these globules will actually have displaced vertices or interesting decays, and so in principle there are interesting signals for these globules. I didn't talk about it, but I just want to flash the reference for this person that did this great work, and you'll see in this paper that global decays in folded SUSY could be an important signal at the LHC in the future. So, however, it's not impossible to imagine that we'll end up high luminosity LHC with some natural parameter space in some theory like identical twin Higgs, and still we haven't seen anything. It's not an impossible scenario, okay? But all of these theories have low cutoffs, below 20 TeV, so experimentally this would point to higher energies, obviously. In theory, it would point to the fact that we need more reasonable U completions, okay? And of course, I pointed out to the fact that there is interesting dark matter model building. Okay, thank you.
So we have time for one or two questions. Yeah. Maybe three, if they are quick.
Could you give me a comment on the dark radiation or effective number of neutrinos? I think in this model, you'd have twin neutrinos or twin photons, and it may conflict with the Planck result.
Right. Okay, so I didn't want to comment on this because we are working on it, but certainly you have to get rid of the. In the identical twin case, you have to get rid of the twin neutrinos somehow. This is non-trivial because you have to get rid of them in a way, you break the Z2 somehow. And so ideally what you do is you break the Z2, because you have to break the Z2 anyway, at the same time, by a mechanism that also gives masses to the twin neutrinos and to the twin photon. That's very ambitious, and that's what we're trying to do. And so you really have to do that because you can imagine that you can get rid of the neutrinos and keep the twin photon, but that's still borderline with structure formation, amazingly enough. So you can get rid of NF is still borderline for 1 degree of freedom like the twin photon, but there's still problems that my collaborators know much more about that have to do with silk dumping and things like that. So I think you have to get rid, in these cases, you have to get rid of the twin photon also. Yeah, you're right.
So in the discussion of natural SUSY, we usually talk about the need at low energies for 3 states, Higgsino, stop, and then at 2 loops, gluinos. But in this context, you're really just talking about the colorless top partners. Is there a reason why I don't have problems in these scenarios with stuff at 3 level, the analogy of the Higgsino, or why I don't really have to care about 2-loop effects, the analogy of the gluino?
So you're talking about the fraternal twin case where I only have...
Or any of these cases, is there a mapping between the natural SUSY language of what we expect for the low energy states? And again, it's Higgsino, stop, and gluino is what we say, kind of 3 level, 1 loop, 2 loop.
So for example, in the folded SUSY, you have the Higgsinos. In fact, they are candidates to dark matter, so you have them there. And then the gluinos are not that heavy. They are at the let's say 1/r, right? So in principle, and in the twin case, in the fraternal twin case, you have the glue is still there. It's not broken at all. So it's not. Yeah, it's not quite a mapping, but the glue is still around. It's confined. It forms all kinds of bound states at low energy, 5, 10, 20 GeV. Yeah, depends on lambda QCD prime. So yeah.
So your point is really to solve the little hierarchy problem and not caring too much about the big one.
I do care about the big one, but if the idea, it turns out that all the neutral natural theories are such that they have a cutoff, and then they are usually such that you solve only the little hierarchy problem at 1 loop. You can do that. And this may be the first step you need to do, but we need to work on UV completions to convince ourselves that this is a sensible low energy theory, of course.
Okay, so you are giving us very good arguments for a 100 TV collider, I see, yeah? So thank you very much, and thank you again.